Sorry about that. I'm going to tell you today about the carbon services of coastal habitats and what those services mean for human and ecological community resilience. So this is most of the work that I did over the course of my PhD. There's some stuff I won't be able to show you, and some work in here that's part of the large collaborative efforts that I also added in just to show you some of the additional data. All right, we kind of have to start at the beginning here. Everybody's seen this figure a zillion times, but we know that CO2 in the atmosphere is going up, and you can see that in the red line there. In tandem, the ocean absorbs about 1/3 to 1/4 of that carbon dioxide each year, and as a result, the PCO2 in the surface waters in the ocean is also going up, which you can see in that blue line. And as the ocean absorbs that CO2, the pH declines and the water becomes more acidic, a process called ocean acidification. As a result of all of those increases in CO2 in the atmosphere and oceans, scientists across disciplines have been measuring both the stocks and fluxes of carbon in various habitats in both terrestrial and marine biospheres. The stocks are shown here in black, so how much carbon is held within a particular habitat, and the fluxes are how much carbon moves between habitats. And both of those stocks and flux values are important to parameterize global climate models and understand the value of these habitats relative to one another in terms of carbon cycling. As we have done that, marine primary producers have shaken out as particularly valuable from a carbon perspective. Kelp forests, seagrasses, mangroves, and salt marshes have all been called out as valuable. In the case of kelp forests and seagrasses, those are submerged, they're in the water, so obviously they can take CO2 directly from the water column, whereas salt marshes and mangroves don't have photosynthetic tissue in the water column, so they don't take CO2 out. And because they're directly in the water column and taking CO2 out, they can potentially provide some sort of buffering service against ocean acidification, which is something that we've explored as a part of my research at UC Davis. In the case of seagrasses, mangroves, and salt marshes, they have a considerable portion of below-ground biomass. Kelps do not have a portion of below-ground biomass. They have a holdfast, so kelps don't contribute to local burial of carbon in the same way that those three habitats do. And that burial of carbon beneath their sediment has been called blue carbon, if you've heard the word. So that's what it's referring to, the burial of carbon in sediment beneath those habitats. Seagrasses are cool because they do both of those things. They can take CO2 out of the water column. They can also bury carbon in their underlying sediment. So most of the work that I did was on seagrasses. I also did a little bit with kelp and salt marshes, but for the most part, the data that I'll show you today is all from seagrass meadows. Worth noting that we're exploring the carbon services of seagrass meadows, but we already know that seagrass beds support a ton of diverse ecological communities, and there are many people at San Diego State that research these critters that live in the seagrass meadows. So they act as nursery ground for all of these species, specific herring, bat rays. There are a ton of invertebrates in seagrass meadows, Dungeness crab, leopard sharks, otters, halibut. So they're important habitats, carbon services aside. They also stabilize sediment and settle out particulate materials from the water column, which can enhance local water quality. And you can see that just if you spent time diving in the seagrass meadows. If you dive on a strong current day, you can see better in the meadow than you can outside of the meadow very regularly because of the way that they can dampen wave energy and settle particles out. So those two additional benefits, can they buffer against ocean acidification? Can they bury carbon in their sediment? And what's their role in broader global carbon cycling are questions that I was interested in answering for my PhD. And this is something that's garnered interest across the state, particularly in California. So when I was working with the Ocean Protection Council in 2014, there was a Senate bill passed, Senate Bill 1363, that sort of brings this potential carbon benefit of seagrass meadows to the forefront of California management. 90% of California's seagrass beds have been lost from things like dredging, docks, moorings, overall declines in water quality, and that provides an opportunity for California to restore some of these meadows to bring the services we just discussed back into California's natural resources. And they in particular called out seagrasses in this bill for their potential to buffer against ocean acidification and hypoxia, which is a little bit interesting because at the time that this is passed, we actually didn't and don't have that much data on whether or not they even provide this service in real time, or if they do, does it translate to improved success for the organisms that we're interested in, dungeness, crab, oysters, shellfish, etc. So in the sort of, with the frame of cart before the horse, we set out to measure the carbon services of eelgrass meadows to try to understand if this would work and how and when. So this figure I'll refer to throughout the talk. This is a summary of the different fluxes of carbon that I measured within seagrass meadows across the state. So there are a variety of different pathways that carbon can move within and among marine habitats near and in a seagrass meadow. I in particular studied these three. So the air-sea fluxes, so how carbon moves from the atmosphere into the ocean over the meadow. The metabolic fluxes, how carbon is absorbed from the seawater or the atmosphere directly into the tissues of the seagrass meadow, and then how they bury carbon in their underlying sediments. We did this throughout the state of California. I only measured all three in one site, which is in Tamales Bay, but the metabolic fluxes and burial and carbon stocks were measured in 5 meadows across the state. Well, 5 bays, 10 or 12 meadows, something like that, across the state of California. Most of the data is coming from Tamales Bay in terms of the air-sea flux work and the metabolism data, but I'll show you a little bit from all the sites in some summary slides. Okay, this is Tamales Bay. This is the site that I was working at. The meadow is on the right there. And you can see, this is where we deployed water chemistry sensors into this meadow. The eddy covariance tower, which I'll talk about in a minute, which measures air-sea fluxes, is on the shore there. And sediment cores were taken in that bed in transects running across the bed and off the edge of the bed. So just to give you an idea of what the seagrass meadow actually looks like. This is a low tide. Typically, not so much of that meadow is exposed, if any, of the meadow. Okay, so that first question, how do seagrass meadows absorb CO2 from the atmosphere, or what are the air-sea fluxes over the seagrass meadow? Typically, in terms of air-sea gas transfer literature, looking at air-sea fluxes in coastal zones, estuaries are cited as massive sources of CO2. So much so that some papers estimate, even though they're only covering a few % of the coastal shelf area, it's enough CO2 production to counteract all of the CO2 absorption that happens in coastal zones. But they're not usually measuring estuaries that are filled with submerged aquatic vegetation of any kind. So in this case, we're measuring the air-sea fluxes over a seagrass meadow in an estuary, and the sort of separate body of literature says that seagrass meadows are typically strong sinks of CO2. So the question being, if you measure air-sea fluxes in an estuary over submerged aquatic vegetation, seagrasses, does the estuary then act as a net source of CO2? So that's our sort of hypothesis here. This is the eddy covariance tower. We set that out in July of 2016. The footprints, the fluxes that it was measuring, extend about 350 meters out from the tower. That changes with tidal height and wind speed, so that's an estimate. You can see the wind is kind of blowing in. You can see from the clouds a little bit. So that blows air over the seagrass meadow and into the instrumentation. And essentially the way this method works is, the way this method works is by taking the air eddies through time in tandem with the concentration of CO2. You essentially get a ratio of how much CO2 moved down over time to how much CO2 moved up over time. And by modeling that together, you can tell if something is effluxing more CO2 or drawing down more CO2, the surface over which you're measuring. And eddy covariance has been applied in terrestrial, Arctic, many different ecosystems for a number of years, which Walt's lab has been doing for a long time. This is the data this is the average monthly flux from each month that the tower was out. So the blue line is average nightly flux, the red line is average daily flux. On the left, on the y-axis is the flux, on the x-axis is the month. Anything over that black line means that the sea surface was acting as a source of CO2 to the atmosphere. Anything below the black line means that the surface was acting as a sink of CO2. The starred data are significant differences between day and night. So you can see the kind of inhale, exhale on both the daily and seasonal scale from this figure. So at night, the sea surface was typically a weaker sink or a stronger source of CO2. And in the summer, the same thing, stronger source of sink of CO2 than it was in the winter. If you put that all together, the surface absorbed about 490 grams of carbon per meter squared per year. That's roughly equivalent to the amount of CO2 that can be absorbed by some terrestrial forests, but there's a pretty big envelope of variability around that number. It sort of begs the question, what's driving those trends? There's some big wiggles in there that make you double take a little bit, so I'll talk about those shortly, but just to give you an idea, the upwelling season, which I'll talk about in a second, and the growth season of seagrass both overlie with those strong summer flux months. But before we can tackle what's driving those differences, you have to understand a little bit about what goes into determining air-sea fluxes. The first thing, which is baked into the equation for flux itself, is the concentration gradient. If the water is oversaturated with CO2 with respect to the atmosphere, just by straight up diffusion, you'll get an efflux of CO2 to the atmosphere. If the atmosphere is significantly oversaturated with respect to the water, you'll get an influx of CO2 into the water. Wind speed is the second component to that equation. If the concentration gradient is set up such that you would expect the water to be undersaturated with respect to the atmosphere, low winds are going to force a weak sink, but as you get windier, the ability for the sea surface to absorb CO2 becomes stronger because you have increased mixing and turbulence. This is that same figure that you just saw on the top, but you don't see the day-night cycles anymore, and now we're starting with January and ending with December, so you can see the shape of that seasonal cycle a little bit better. On the bottom, you see the average wind speed. So we know that wind is important to the fluxes, and you can see that in the months when the wind speed increases, you get a stronger sink of CO2 in those months. But in order for the wind to act on the potential sink of that water, you have to have something that also sets up that concentration gradient. So biological activity is one thing that can set up a concentration gradient such that organisms in the water are absorbing CO2, which decreases the availability of CO2 in seawater and can increase the difference between the concentration gradient between the atmosphere and the ocean. This is upwelling index. Upwelling occurs on our coast, and I'll talk about it in a little bit. Probably most people in this room know what the upwelling processes are on this coast, but you get a big pulse of high CO2, low oxygen, cold, nutrient-rich water when upwelling occurs. And upwelling peaked strongly in May and persisted through September during the time that the tower was out. And you can see from other data that trace a parcel of water that is upwelled and looks at what happens after that water is upwelled. Initially, you get a big efflux of CO2 to the atmosphere because it's coming up with deep CO2-rich water. And then in the days and weeks following that efflux of CO2, the nutrients in that water contribute to primary production, and then you see a strong sink of CO2 as primary production can catch up with those nutrients. So we know from previous publications from Tomales Bay that that water gets ejected into the mouth of the bay and moves through the footprint of our tower in the site. And we can see in May, right when upwelling peaks, you get this sort of increase. You would kind of expect this data to be down here, but it's not. And probably there's an upwelling signal in there where high CO2 water comes into the bay, and then before phytoplankton concentrations can increase and primary production can increase to take advantage of those nutrients, you get the signal from the upwelled water. So those are just sort of physical processes that are driving those air-sea fluxes, but can we actually attribute those air-sea fluxes to the seagrass beds beneath? And you can reasonably assume that the seagrass meadow, since it's right underneath that flux tower, is going to be contributing to the air-sea fluxes, and that's reflected in these biomass trends from the meadow. The biomass in winter of seagrass is around 50 grams per meter squared, and in the summer it's quite a bit more variable, but 250 grams per meter squared. If you put all these data into a model, day length is a strong correlate with air-sea fluxes, so the longer the sun is out, the more biological activity can occur, so that sort of follows naturally. But to better address the question about whether or not the seagrasses and the water chemistry are influencing those air-sea fluxes, we also put sensors into the meadow at the same time. So that gets at this more mechanistic view of what's driving those fluxes, but it's also answering that additional piece about whether or not the modification in seawater chemistry that the seagrasses are doing can meaningfully increase the pH such that they're buffering against ocean acidification. We have to take a quick step back to look at the OA chemical equation just to get a more mechanistic view of this, but probably you already know this. CO2 goes into the atmosphere, reacts with water, it produces carbonic acid. Carbonic acid dissociates into bicarbonate ion and a proton, or a hydrogen ion. That hydrogen ion goes back and reacts with carbonate ion on the bottom here and forms more bicarbonate. So carbonate is a building block for shells, corals, oysters, etc. And as we produce more and more bicarbonate and we decrease the availability of carbonate ion in seawater, it becomes challenging for any calcifying organism to grow. So that's sort of the mechanism behind all of the CO2 degradation in shell building organisms. California is naturally acidic, and so we've already been exposed to levels during times of upwelling that won't be observed in other parts of the world until 2100 or further. But we know that it's not isolated. There's a mosaic of pH, low and high pHs across the coastline, and some of that is driven by upwelling, and some of that's driven by chemical stress from eutrophication, from runoff, increased nutrients. So there's sort of two veins of thinking on whether or not OA is going to be more or less problematic in California. Will it be more problematic because we have extremely stressful chemical conditions, or will it be less problematic because our species on the coast are already adapted to varied high pH, low pH chemical conditions, so they'll be better equipped to handle that. And from what we've seen so far, there have been existing negative impacts already observed from additional OA-induced stress along our coastline. So these are pictures of oysters that have been exposed to corrosive waters over time. This happened in the field. This is not lab data. And so we can see decreased calcification. We can see physiological changes. There are behavioral changes that occur in many different organisms, decreased growth, survival, shell thickness, etc. And all of those things have had socioeconomic consequences on the coast already. Whiskey Creek Oyster Hatchery in Washington, there was a big interest in 2008 to understand why their oyster hatcheries were crashing, and this has motivated a lot of that legislative work that you've seen in California so far, because they could not figure out what was driving these crashes. They looked at disease, they looked at a whole bunch of different factors, and ultimately settled on the fact that during times of upwelling, the conditions are now more stressful due to anthropogenic carbon than they have been in the past. And that is what led to the really detrimental effects to the whole West Coast oyster hatchery in Washington and Oregon during those years. And that motivated a whole bunch of this work. So the running hypothesis then is, given we know that carbonate ion concentration is important to shellfish, if in the presence of seagrasses, CO2 concentrations go down, does that increase the availability of carbonate ion in the seawater? And then does that translate to happier, healthier, meatier oysters? To do this, we put oxygen and pH sensors out in the seagrass meadows. These are CFOX sensors that measure oxygen pH, temperature, salinity, pressure, to get a really good look at the chemical conditions inside the bed, and then comparing them to the conditions outside the bed. What we would expect is something like this. So during the day, they're taking CO2 out of the seawater for photosynthesis, but at night they're respiring, so they produce CO2. So you would expect greater variability inside the seagrass meadow in both day and night, because at night they're producing CO2 and during the day they're consuming CO2, and then you might expect to see some sort of dampened signal outside the bed because there's still productivity happening in the water column, there's still phytoplankton, so you won't expect that diurnal signal to be completely gone, but you would expect the change in amplitude. But the question is whether or not those dashed lines you see in the middle are indeed shifted above one another, or does nighttime respiration fully take into account the same exact effect that you saw during the day, such that their average lines are one on top of another. So that's a big question that means a lot of different things to organisms. This is a look at the data from the single deployment that we did into Monmouth Bay in the summer. This is dissolved oxygen. So you can see from the data that yes, the predominant signal is that the variability inside the meadow is much greater through time. And then the means, if you drew a line through those, the dissolved oxygen is indeed significantly higher inside the seagrass meadow than outside the meadow. If you take a look at the pH, the effects are more variable. So the variability in chemistry is larger inside the meadow, but there's a varying effective mean, or a varying mean pH through those two systems through time. In the winter, you see increased variability still inside the seagrass meadow, although less than you do in summer. Same thing with DO. You do see increased DO inside the seagrass meadow compared to outside. And again, with pH, there's a varying difference in mean pH through time, depending on whether or not you're inside or outside the meadow. So if you look, though, at the correlation between those water chemistry data and the overlying fluxes, it's noisy, but you can see that as dissolved oxygen inside the meadow increases, so typically dissolved oxygen increase is associated at roughly a 1-to-1 ratio with a decrease in carbon. So as increase in DO occurs, decrease in carbon, you do see an increase in CO2 absorption at the estuarine surface. We ran some time analyses on these to see if there was any lag. So if photosynthesis is happening, or if the DO is increasing in the meadow, does that then lead to an increase in CO2 absorption at some future time step? But we didn't find any significant lag, so it's only significant at the time. So that means that the change in CO2 or increase in oxygen in the meadow is leading to a fairly rapid, within the hour, increase in CO2 at the sea surface. So those time series that I showed you were only 2 deployments in a single meadow. And what we did was that same experimental design with meadows in the seagrass bed paired with sensors in the seagrass meadow paired with sensors outside the seagrass meadow across the state of California over the course of 4 years. And this is the results from that entire data set for both pH and DO. The pink bars are all the data from outside the meadow, and the blue bars are all the data from inside the meadow. You can see we have a ton of data, 60,000 count there. I think that's 15-minute frequency data. And we do see, when you look across space and time, that the pH inside the seagrass meadow is typically higher than outside the seagrass meadow. And the average difference between pH inside seagrass meadows and outside is about 0.084. Seems small, but pH is on a log scale, so that translates to about a 20% decrease in acidity inside the seagrass meadow. And in some cases, that can last for up to 20 days. So the bottom point is important, because if it's less acidic inside the seagrass meadow, but it's varying really rapidly such that you get really corrosive conditions and then really favorable conditions, it might not be meaningful to an organism. But in this case, 20 days is a pretty substantial period of time to be buffering against ocean acidification. And those findings have a lot of management implications, which we're just sort of starting to tackle. So yes, they do ameliorate ocean acidification, seagrass meadows. There's some really interesting latitudinal trends that I'm not going to have time to talk about, but we're starting to pick apart which seagrass meadows do this better and why. What are the drivers? Is it the residence time of seawater, the biomass, hydrodynamics? So those kinds of questions will provide more utility for this kind of a service if you're an oyster grower, for example, or just interested in habitat restoration for that service. We have brought this into the lab and varied seagrass shoot densities and looked at the response of oysters growing in those varied shoot densities and then measured the chemistry associated with those. And this is something that we'll be submitting to ecology this week or next week. So we did see a positive effect between oysters and seagrass density facilitated by increased pH in mesocosms. So it still remains to be seen what the response is from oysters in the field. Okay, switching gears to the last flux, we talked about air-sea fluxes, we talked about metabolism. Now I want to briefly talk about the carbon burial that occurs in those same seagrass meadows. So this service happens on a slightly different time scale. We've been talking about air-sea fluxes and metabolism, which is rapidly absorbing CO2 from the sea surface and out of the water column and changing the CO2 concentrations on this minute to daily, maybe max seasonal scale. But in the case of this carbon burial, you get really low rates of carbon sequestration in sediment. So the sediment accumulation rates are like 0.15 to 0.2 centimeters of sediment per year. So really slow rates. But the carbon that's buried in that sediment is a lot less labile than carbons that would be absorbed at the sea surface. So it's in the form of organic material. And the reason these habitats are particularly good at doing this is because they're inundated, they are wet, so there's low oxygen in those sediments. And because the oxygen is low, you get limited decomposition of that organic material. So in the case of a forest, for example, the tree is absorbing CO2 from the atmosphere and it's holding onto that carbon for its lifetime, and then the tree eventually dies and a lot of that carbon is remineralized and converted back to atmospheric CO2. In wet environments, the same process happens. When organic tissue is deposited into the seagrass meadow, some of that carbon is remineralized, but as sediment accumulates on top of that carbon, it inhibits degradation due to low oxygen, and some of that material is ultimately buried and sequestered for millennia in sediment. So it's a slightly different, slower timescale process than the other carbon fluxes that we talked about, but it can be sequestered for millennia. And this is something that we know all of this information from other studies, but in California we've been lagging a little bit. Until recently, there were no published studies on seagrasses and their carbon burial potential in California, and then a publication came out 6 months ago or something with Kevin Hogle, who many of you know, that did measure some of the carbon stock assessments in seagrass meadows. And there's only a few from salt marshes, and most of those papers are pretty dated and from 1 or 2 isolated marshes in the state. To do this, we went out and we took sediment cores just with pieces of PVC inside the seagrass meadows. We also did this in salt marshes, so switching gears to salt marsh and seagrass meadow here. Took them back to the lab, slice them up, and do a variety of analyses on those core subsamples. So we have almost 90 cores from across the state and about 727 subsamples from all of those cores. If you look at just our data, so that's in blue, you can see that the salt marshes definitely store a lot more carbon in sediment than do seagrass meadows and nearby bare sediments. But we actually didn't find any difference between the amount of carbon stored in seagrass meadows and unvegetated sediments nearby. And I can talk about that shortly. The seagrass meadow, if you actually quantify it, it's about 11.5 kilograms of carbon per meter cubed in sediment, and salt marshes 32, bare sediment about 12, although the meadow and the bare sediment didn't differ from one another. To put those into context about what they actually mean, I used some of the published data from reviews on the subject. I think this is a 2015 and 2017 paper, so they're fairly recent publications. Our salt marshes in the middle store not significantly different, but at first glance a little bit less carbon than do the salt marshes, but they're comparable. Seagrasses store significantly less than do global, these are all global estimates that I'm comparing them to. So our seagrasses store significantly less than global estimates of seagrass carbon storage. And then for bare sediment, we found significantly higher carbon storage potential in our bare sediments. The differences driven by the seagrass on the far right over there, part of that is because Posidonia species, which is a species of or a genus of seagrass that lives in Mediterranean Australia, they're really good at burying carbon in their sediment. They have massive below ground biomass mats that you can see a picture of over there. So when you remove the Posidonia genus seagrass from those seagrass estimates, our data are actually kind of on par with global estimates. So it is skewed a little bit by Posidonia. If you look at rates, so I measured sequestration rate, so not the amount of storage in the meadow, but the ability for it to sequester, so the fluxes of carbon into the sediment. And in seagrasses, it's about 15 grams of carbon per meter squared per year. And if you take a look, this is from maybe 10 cores of salt marshes in California. It's 173 grams of carbon per meter squared per year. So the rates of carbon sequestration are quite a bit faster in salt marshes than in seagrass meadows. To contextualize, these are rough numbers, but I added up from a mapping tool the total area of seagrass and salt marsh habitat in Tomales Bay and then multiplied those by those carbon stocks to try to put it into meaningful language. The top meter of Tomales Bay sediment, seagrass sediment, stores the equivalent of 30 million miles of driving. So maybe that means something better than the stock assessment. The rates, so even though they're much slower than salt marshes, the seagrass meadows still absorb carbon at a rate that's about 4 times faster than than terrestrial forests, and that's from a review published in 2011. I'm going to skip that last one for a second. Salt marsh stocks were larger than most terrestrial soils. If you run those same numbers, those are just from EPA standards on vehicle emissions. You get the equivalent of about 46 million miles of salt marshes. And those numbers are closer to one another, not because the salt marshes are not as, they're much better, but there's less salt marsh area in Tomales Bay than there is seagrass meadows. And then if you compare those salt marsh rates, it's about 27 times more carbon annually sequestered in salt marshes in California than in seagrass meadows, than in terrestrial soils. So these last 2 bullet points, if you use those sedimentation rates, what those mean is that it can take, in the case of a seagrass meadow, 666 to 500 years for a meter of seagrass sediment to accumulate. And in a salt marsh, it takes about 90 years for a meter of sediment to accumulate. So if you think about that, really that begs for conservation over restoration in terms of carbon stock assessments, because if you restore a seagrass meadow for its carbon services, the conserved bed has the jump on you by 500 to 600 years before you can get back to the original amount of carbon stored in those seagrass meadows. And this has been published multiple times in various different ways that creation of emission or risk of emission of carbon from surface sediments is really, really high because you're just remineralizing carbon that took hundreds of years to accumulate in surface sediments. And this paper actually went so far as to calculate the economic costs of that carbon emission ranges on $2 to tens of billions of dollars in carbon costs. The last piece of this is looking at drivers of carbon storage in sediment. This is a figure of the amount of